Okay, so now we've really getting into the thick of GD&T and form controls, and specifically straightness. We've seen the concept of a surface element, a derived median element. We've talked about material condition and how we're going to use that to adjust the tolerance zone. And we've also had a couple examples of thinking about and actually drawing the nature of the tolerance zone, whether it's two parallel lines, a cylinder. You're going to see as we go along that the tolerance zone can be a lot of things, almost an infinity of things. It can be parallel lines, it can be parallel planes, it can be a cylinder, it can be two concentric cylinders. And when we get into complex forms, let's say a gear tooth or something like that, the tolerance zone can actually follow pretty much any curvature or any variation that we can define with a dimension. So the tolerance zone is ultimately under our control. That's what we wanted with the feature control frame. We want to be able to do it compactly, but we want to have control of all those aspects of the tolerance zone. And what we're going to talk about now is really the ultimate control of the tolerance zone, which is allowing it to float. Its size can be adjusted depending on conditions, and those conditions almost always are conditions of the material. In other words, how much material we have to deal with. I'll explain here in a little bit why we would want to do that, but this is the how of we do it. Okay, so if you look at figure 5.3 in your handout, this is basically the same shaft. It's still a 16 by 15.89 diameter shaft. Again, I'm going to be probably thinking in terms of thousandths, just so it's a little bit easier for me to deal with. If you can think about it in metric, you can certainly do that. A number is a number. The unit has no effect on anything. Okay, now if you look at this, right away we can start making some determinations and start evaluating this geometric requirement and the nature of the tolerance zone. We've already seen this before. We see that the one symbol is in the box. It is a straightness control. Now we have to determine whether it is a surface element or derived median element. It's adjacent to or attached to a feature of size, the diameter of the shaft. So we know it's a derived median element, which is this center line. We know that it is a diametral tolerance zone, so it's a cylindrical tolerance zone, 40 thousandths in diameter. And the only new thing here now is this M, which stands for maximum material condition. We call this a material condition modifier, along with this. Those are the two existing material condition modifiers. Now, stepping back though, I told you that at one point there was this that meant regardless of feature size. And in the previous examples where we had no material condition modifier, in the old days you would actually see this. The regardless of feature size symbol would actually be there. This, again, because of the way they interpreted it, it was a source of confusion and really unnecessary, because if there is no symbol there, you can assume that it is regardless of feature size. So I always tell all the other classes that if you don't see anything over here, any material condition modifier, you can sort of imagine that there is a regardless of feature size. What does that mean? That means that the tolerance zone as defined in the feature control frame does not vary. It is irrespective of any size variation. If you have a 40 thousandths diameter tolerance zone, that's all you get. You get 40 thousandths. It doesn't matter whether the shaft is at its largest or at its smallest, the tolerance zone is invariable. In this case, we have a maximum material condition modifier. And now we have to take an extra step. And that extra step is evaluating what is the nature of the tolerance zone with respect to the material condition of the shaft. Well, what material condition can we have? We can have this. I'm going to put an extra zero there just to think in thousandths a little easier. And we can have this. And anything in between. Now the difference between these two is that right? I think that's right. And that difference again is called the allowance. So just sort of keep that in mind, is that you may be at the upper limit, at the maximum material condition limit. You might be at the least material condition limit, but more likely you're going to be somewhere in between. And that has an impact on how we evaluate this statement, this GD&T feature control frame. How do we know that this is the maximum material condition limit, the 16? Well, it's a male feature. It is a shaft. I guess in one regard, doing this on video here is a little bit better than in a classroom, because whenever I talk about material condition and shafts and holes and that, I will sort of get an undercurrent of giggles. But we do have to think about it in that sense, is that this is a male feature of the shaft, and it has at its maximum material condition is the biggest it can be. In other words, that shaft has the most material in it. It is going to be at its heaviest. Now, how does that play out? How does this relate to this? Fairly simply. When you have a material condition modifier in the feature control frame adjacent to the tolerance zone size, that means that that tolerance zone is 40 thousandths when the feature is at maximum material condition, and only when the feature is at maximum material condition. So, if this actual shaft that we actually made and measured was right at 16 inches in diameter, the cylindrical tolerance zone about the center line would be 40 thousandths in diameter. If the shaft is at 16 inches at its maximum material condition. If it is not, now of course the only way it can go is it can only get smaller all the way down to 15,890. If it is not at maximum material condition, the tolerance zone changes in size. This is a powerful, powerful feature. I'll explain why in a minute, but how do we evaluate that? Let's make another shaft, and let's make sure that we don't hit it right at maximum material condition. Let's just take it down . Let's take it down 1/1000th of an inch in diameter. So the next shaft that we make is at 15.999. It's 1/1000th of an inch smaller than its maximum material condition. And now we got to say, well, we know that at 16 inches the tolerance zone for straightness is 40 thousandths. How big is it when it's 1/1000th less than maximum material condition? And it's real easy. We look at the difference between the actual and the maximum material condition. In this case it is 1/1000th. If the shaft is a thousandth smaller, the tolerance zone becomes a thousandth bigger. So it's a give and take. You take a little bit of material off, the tolerance zone can be on a one-to-one basis, thousandth for thousandth, it becomes larger. That's all there is to it. All the way down to, we can keep stair-stepping down, adding thousandths by thousandth here, such that if the last shaft we make, let's say our tool is starting to wear, and over the run of the parts, the next shaft we make is, or the last shaft we make is 15.890. We lost 110 thousandths on diameter. Definitely probably should have sharpened our tool somewhere along the line, but we didn't. We have 110 thousandths allowance in the tolerance. How big can that tolerance zone get? It becomes the allowance plus the original amount. So in other words, if that shaft is at its least material condition, the tolerance zone becomes 150 thousandths. Okay, now I don't know that that's obvious why that would be useful, but let's think about it. Let's say you're using these shafts, you're making them for a reason. They're going to go into a bored hole somewhere. You're going to slide this shaft through a couple holes, or through a hole to attach a gear or a pulley or something. And the hole obviously has a size too. And let's say that if the shaft and the hole are at their maximum material condition, in other words, the hole is at its smallest and the shaft is at its largest, in order for that to slide through, it's going to have to be pretty straight. If this shaft at its maximum material condition has a banana like that, well, you're just not going to be able to shove it through that bored hole. What would you do if it didn't? Well, you'd do one of two things. You'd open up the hole, or you'd remove some material on the shaft, and by doing that, eventually you're going to get enough clearance to shove the shaft through that hole. You do the same thing at home. Let's say